Thank you, Emilian. This talk is in two parts. First of all, on patches of flexible surface and the airflow or sea flow over them, and secondly on aspects of storms. It's joint work with some colleagues here at UCL, including Ted Johnson, who's in the audience. If any problems arise, then please ask Ted. Okay. And also a colleague, Ulrich Rothmeyer, in the States. The aim of this work is to get reduced equations instead of the Navier-Stokes, as a complement to the Navier-Stokes, as it were, and try to understand more of the physics and perhaps mathematical structure within these sorts of interactions. So let's get going then on the flow of patches of flexible surface. We realise in the background that the flows are complex and the ice properties even more so. We're thinking of airflow over ice or sea flowing under ice, but whether we're actually there or not remains to be seen. The Reynolds number is going to be typically medium to large. What we aim to do is to incorporate viscous effects wherever they matter, and nonlinearity and incident vorticity in the oncoming air or water flow. As part of that, tentatively we'll assume the flow is laminar as well as unsteady and three-dimensional. Okay. So the particular situation we're going to look at involves a large Reynolds number up there based on a development on a streamlined length scale, typical length scale AD. D denotes dimensional quantities, and what else? We'll suppose there's an incident flow coming along, which may be a boundary layer, but anyway it's got thickness, say delta, and an atmospheric thickness, for example, could be anything between 10 to hundreds of meters. So that's the rough guideline. If we take the development length of the boundary layer itself to be our representative length scale, then that delta is of order Reynolds number to -1/2, the classical thickness. And it will have an oncoming velocity profile u0, which depends on y, the vertical direction, and that will have a shear at the wall, lambda, which will be a function of time in general, and an upper end value at the top of the boundary layer or top of the flow, which is some order one value locally. We're then going to look at patches that are relatively short compared with that long length scale. So there's length scale, relative length scale L, which is small, and as you can imagine, if the length scale is smaller, then viscous effects, the viscous sublayer tends to be concentrated near the wall. The way it does so is with an L to 1/3 dependence on thickness, and so we've got a viscous sublayer near the wall, and we've got fast flow outside. The question then is, does the sublayer matter or not? Is it a primary or a secondary effect on the interaction with a flexible patch? We're going to address here cases where it's a primary effect. In fact, that means the length scale L satisfies certain restrictions on as regards the Reynolds number variation. If the length scale is as short as that guy, then we'll get the full Navier-Stokes equations holding in a tiny weeny region, which might be millimeters. If we got to that length scale, then there's interaction between the sublayer flow and the outer flow. This is where triple deck theory comes in. So we're going to look at slightly shorter length scales and see what happens. Blah, 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 blah. Okay. Okay, so there's the scenario. Two-dimensional oncoming velocity profile with shear lambda at the bottom here. We'll be looking at what happens in the sublayer. Within that sublayer, the patches are present. This is meant to be a three-dimensional picture. So y is the vertical, and then z and x are in the horizontal. The oncoming flow is in the x direction. These patches are they could be randomly placed, but in fact we'll be taking them as periodic in the span, that's the z direction, and perhaps a row or two in the x direction. What else do we need there? There's our length scale L, and that's about it. So we then substitute an asymptotic expansion into the Navier-Stokes equations, and that leads us to the form of the boundary layer equations with certain boundary conditions. We're also going to assume that the flow is quasi-steady at first. It will become unsteady later on. And we're going to include a wall flexibility model, which is of the sort that Sasha and Emilian and Paul Brocklehurst and Jean-Marc and colleagues have spoken about before. Yeah, the governing equations then is this system here of interacting boundary layer equations. So it's the full continuity equation in 3D, and then the full inertia and acceleration terms on the left, pressure gradient. The viscous term is predominantly d2u dy squared, as is usual for a boundary layer, and similarly d2w dy squared. U is the velocity in the x direction, w is the span-wise. And the normal, the vertical momentum equation is simply dp dy equals 0. So the pressure is an unknown function of x, z, and t. The boundary conditions are what you might expect. It's no slip on the surface, the disturbed surface, including the patches. I should say here the y we're using here has been displaced to be it's 0 is along the flat surface and then on the top of a hump or flexible patch and so on. So it's no slip condition there, and then matching at the top is basically that the flow must go back to two-dimensional, just the uniform shear as we move away from the patches vertically or horizontally. Just uniform shear. The sublayer C is only the bottom part of the boundary layer. And then there's a wall relation between the unknown shape F and the unknown pressure P. So it's E1 delta the fourth of F is equal to the pressure difference. P naught is a base pressure that's prescribed, and E1 is proportional to the flexural rigidity here. While we're here as well, just note nonlinearity appears in the flow equations in those inertia terms and not in the wall relation. Okay, now if we knew the shape F, then we would know what to expect from that sort of flow, boundary layer flow. Here are some results from a couple of decades ago. Flow over a fixed hump. So the flow's coming in as a uniform shear, and a lot of it goes over the top of the hump. Some of it goes around the sides, and then downstream you get corkscrew, horseshoe vortices. And along with that, here's a picture of the wall shear, the local wall shear. Everything we're talking about here is local. The shear comes in as this value lambda upstream, and then over the front face of the hump, as you can imagine, the shear goes up, and then on the leeward side it goes down. And for this height h of 2.8, scale height, the descent is such as to produce reverse flow or negative shear in the lee of the hump. So there's flow reversal, and then we're into the corkscrew eddies. However, we don't know F for these flexible patches. So let's talk a bit about the techniques involved to try and solve this system. We're going to assume it's quasi-steady at first, so neglect d by dt. That will come in later. And we're also going to begin with small disturbances. So it's a very mild start. We'll see that nonlinearity comes in later as well. And then we're going to tackle that system using something called the skew-Shears method. And okay, let's just jump into it. There are probably too many details here, but yeah, so we're looking for a small disturbance about the uniform shear lambda y. Everything's expanded in powers of h. H is small. So we end up with virtually the same system as before, except the nonlinear terms linearize. So there's u du dx becoming lambda y du dx V du dy is V lambda, all the same, and I think everything's the same there as you might expect. The forcing is from the F at the top, F displacement, and then related to the unknown pressure. Oh, and F, yeah, the boundary conditions at the edges of the patch are what you might expect. Zero shape F, zero height F, and zero derivatives. Oh, I should have said also, yeah, and we've dropped the d by dt, that's gone. So for we've now solved that system. It's a little bit awkward, but not too bad. Solve it by, as you might imagine, solving the flow half first, and then the wall half second, and then iterating on and on. We use a skew Shear's method, which involves defining quantity capital U, capital V, which are related to the real shears of the flow. And then the three-dimensional problem can be reduced to this two-dimensional form here, with an effective pressure capital P, which is related to the real pressure. And then the boundary conditions become these, which again are two-dimensional. So this is a 2D problem. There's no z derivative in it, for instance. And we can then get the solution from a Fourier transform approach, and it's written down here. It's an integral form. So this effective pressure is given by a convolution integral over the hump. The hump or the patch goes from x1 to x2, say. Its shape might depend on z. But anyway, it's this integral from x1 to x. Gamma here is a constant. It involves the Airy function. It's a positive constant, and it also involves the factor lambda. Yeah, there's no upstream influence in this quasi 2D problem. So P is 0 upstream, then it's that, and then there's a wake effect. Once the F stops, then there's an algebraic decay in the wake. Okay, now this, so given, if we know the shape F, then we can work out this effective pressure, capital P, and then we get capital P, get the real pressure, P or P star, from solving this force Laplace's equation for P star. That comes because to get to this 2D version, we've taken the x derivative of the x momentum equation plus the z derivative of the z momentum equation. Hence we get pxx plus pzz. Yeah, so we can do that. So that is a way to solve the flow half and come out with the pressure. And then for the wall half of the problem, it's the other way around. Given that pressure, we have the right-hand side here, the pressure difference involving E1, and this is essentially solving delta force F is equal to the pressure difference, which one can do in various ways. It's a stable process, and then iterate between the two halves of the flow. Okay. The case I wrote down has only got that factor E1 in, which is the flexural rigidity. We could add in other terms to accommodate mass density, damping constant, spring stiffness, longitudinal tension, these terms here, into the same routine. But we decided to focus just on the flexural rigidity effect. And you can treat random arrays as well, and many patches in principle. We do many things in principle. But first we'll focus just on one row to try to understand a bit more. So here's the first solution that came out. It shows the shape F of the converged solution against x. It just goes from -1 to 1. Certain parameters are written down here. That's the base pressure. That's the span in the z direction. It's 1.25. The span of the period, the whole periodic array, is 5. Anything else there? Yeah, just one row of patches. And the solution does what you might imagine. As the flow's coming towards us, then on the side of the patch there's very little disturbance. That's this sort of effect. And then as you come towards the middle, the effect gets larger and is at its maximum in the middle. The shape is not particularly outstanding. It's just like a parabola that's a bit bent towards the edges. And all the solutions we got have got basically this form. It's really a question of how high the hump goes as the parameters vary. Okay. So that's the shape that comes out. This is showing the pressure or pressure difference that comes out for that case. Now it looks a bit of a mess. What we've got here are solutions for the pressure curves at different z for 3 different grids. The difference between the grids is that the x infinity has been increased and increased. And what soon became clear is that we can get the pressure solution above the hump between plus and minus 1 very easily, but there's a strong wake effect and upstream effect which is dependent on the conditions far upstream and far downstream. Do we need to say more on that? That's it. Here's another solution where we've now increased the width of the patch and up to 2.5. Previously it was 1.25, if you remember, and it's a very, very similar shape again, but also again, okay, the patch shape is pretty insensitive to the grid used, but there is obviously a pressure effect outside, outside which has got to be explained. At that stage we decided to try a mode analysis to try to get at this, this strange effect of the pressure and anything else we could find. So now we're looking for a solution which is, in terms of modes, e to the I beta z summed over beta, and that's going to deal with the z dependence and substitute in. And that's rather nice because it converts all our PDEs to ODEs, as shown there. That's the P star related to capital P. This is P star related to F or F star. This is the wall relation. This is the del squared of P star equation. And these two are coupled with the integral equation we had before. So it's an integral differential system. We can solve it analytically, subject to boundary conditions, and solve it for any beta. And that's kind of helpful. I'll show this result first. So this is for a particular lambda, which is fixed at 50 and varying beta from 0, the two-dimensional case, upwards to 4. Okay, and the what is shown, what's happening here is that at a fairly small beta, there's a distinct change from the two-dimensional result. Here's the 2D result, which we mentioned before. The two-dimensional case has no upstream influence, so pressure starts at 0 there, gets to here at the trailing edge or downstream edge, and then there's an algebraic effect. The three-dimensional result has upstream influence, and because the pressure is non-zero, there's an exponential upstream influence, and then there's a longer decay downstream, and likewise for the other betas. From the analysis, you can show that yes, that the 3D case does approach the 2D case over the patch perfectly fine, but the approach is slow. It's a beta to the 1/4 dependent, so that's why there's still quite a gap there. And then the long upstream influence, sorry, downstream influence and upstream influence is due to the exponent beta being small. It's kind of saying that for small beta, the patch is quite wide, so there are two length scales in the streamwise direction. One is the length scale of the patch itself, which is order 1, but there's also a longer length scale comparable with the wide span. So you get a length scale of order 1 over beta. So that was kind of comforting as regards the pressure results before. But also with this mode analysis, as you vary lambda, so here we're showing 150, 99, 150, 99. As you go on increasing lambda up through the 80s, the corresponding shape f gets larger and larger, and in fact tends to infinity at some finite value of lambda. There's the plus infinity, and you go on increasing that lambda through 85 or something, 83, 85, the solution comes back at minus infinity, and you get to this at 99. At 109, the solution would be less. So there's a resonance occurring. This is showing a typical property of the shape f. It's the value in the middle plotted against lambda, and as lambda goes through 83 point something, the height f goes to plus infinity and then comes out at minus infinity. Other cases are found to give resonance as you put in the other factors like the mass factor and so on, damping constant. There's always a resonance. This particular example here has a resonance at lambda is 58.5, somewhere there, similar to what we saw before. And then another resonance at lambda is 235. There's a whole sequence of shear values which produce this resonance. Okay, now with resonance occurring, that immediately suggests that nonlinearity can come into play very easily, or some other physical effect is going to come in close to these resonant values, and nonlinearity is a good candidate. And it does so with the time scale being slightly shorter than what we started. We started with a very long time scale. Everything was quasi-steady, and now we have weakly nonlinear effects coming in around a resonant wall shear, and also the time scale gets shorter than what we assumed. And well, we do some analysis around that and end up with this amplitude equation. This is the amplitude of the hump, scaled amplitude of the hump height, or the pressure response, or the wall shear locally. Yeah, dAdt plus a squared is equal to this value P2, which is the base pressure constant. So a very simple equation to solve. This is the phase plane results. Just to match up with what we had before, so what we started with in the first stage was we had 0 d by dt, dAdt was negligible, and a squared was negligible. It's simply a equal to the a coming in at the something related to the pressure. Okay, so looking at the solutions of that system, it's probably easiest just to think of time marching, and here's an example or two. So against time, we're plotting the amplitude A. The solution comes in on a quasi-steady state, QSS, quasi-steady state, and there are two options. It can march forward in time and end up on another quasi-steady state at higher times. So this corresponds to going into resonance and then smoothly through on the other side. So the nonlinearity disappears once you come out at larger times. The alternative, though, is that the solution starts on the quasi-steady state that we've been looking at, and then goes into a singularity at a finite time. So A goes to minus infinity there, and also in these cases here. You can see that can happen in the equation, of course. The dAdt balances off against a squared, and that will give you a singularity, a blowing up like 1 over time, 1 over t naught minus t, as t tends to t naught. Okay, so that was those results were for one row of humps, and we get similar resonance occurring for more. Here are four rows present, and we're getting the impression it's a general property of arrays of flexible surfaces. Okay, so stage one was linear and quasi-steady. Stage 2 we've just been through was weakly nonlinear and unsteady, but then can blow up. So the stage 3 then is of interest. The singularity is such that we get right back to the original system. I'll flip back if possible. We get back to this this full system here. So we get full nonlinearity occurring, full unsteadiness, and all these boundary conditions are in play. Again, on a shorter time scale yet. This is stage 3. All we've lost really is the P0. The P0 was the forcing, and that's done its job. That's no longer active. Yeah. So now we've got the picture that's coming out is that if we plot representative quantities like the local wall shear stress or the patch height against time t, then there are two possibilities. If the incoming shear is subcritical, then nothing much happens. The solution original disturbance stays small and quasi-steady. But if the oncoming shear is increased, then the solution is supercritical, and that can then lead on to from stage 1 to 2 to 3 and so on. Faster and faster timescales, full nonlinearity up here in A, and then even that system can break up within a finite time. You're starting to get a sort of cascade of smaller and smaller scales, and vortex roll-up occurs, and it's taken to be getting into deep transition. So that's a transition that occurs in the flow, but also to some extent in the shape of the hump, shape of the flexible patch. I'll just finish this section off quickly with just checking on a few words. I think we've been through most of this. We don't need to look at the details, but so we're getting flow and shape transition. The effect is a bit like a turbulent trip. So at certain critical flow speeds or lambdas, the hump shape can pop up and act like a trip on the flow. Both shear and wall flexibility are required. So if you took away the shear and just looked at the wall modes, they're not that unstable. If you took the wall flexibility away and just looked at the shear problem, then the flow would be completely stable. It's the combination that produces this resonance, and it's also a non-standard path into transition from low amplitudes. The length scales involved are quite different from the known length scales of flow instability. Like, it's different from Thormy-Schlick-Team or Gert the vortices or anything like that. Okay, well, I'll finish off with part 2, which was motivated by thinking about storms and could we do anything helpful there. The answer is probably no, but let's see. So the sorts of problems we're looking at here involve fluid-body interaction. So we've got flow coming along here. It could be a uniform flow or it could be a shear flow over a solid surface, and there are there's debris or ice shards or dirt, various particles in the flow. It could be any number of them. We'd like to know what happens to that flow, to that sort of flow. The motivations are from aeronautics and biomedical and environmental. And we're going to use again scaling and analysis and computation on some reduced systems. Okay, I'll go through 2 or 3 cases just to show you what we've done, not omitting the details, and then focus at the end on one little case which might be of interest. So here, this is looking at a long body in a boundary layer or channel flow, and having it interacting with the oncoming velocity profile. yep, the interaction produces instability. That's what you might imagine if you're putting a body into a fast flow in a boundary layer or in a free stream coming along, and if the head goes up, then the head is likely to go up. It's likely to be an unstable situation. Or the head goes down, then again it goes down. And that's what you find in this model. In virtually every quantity you can think of. This is showing the height h of the centre of mass of the body, and also the wall shear. Lots of instability, exponential growth at large time. We're surprised actually though that you can this situation can be stabilised in at least three ways. For instance, if the particle is front heavy, if its centre of mass is 10% off being in the 50% chord, and that's enough to stabilise. It produces waves instead of exponential growth. Likewise, if the particle is flexible, responding to the local pressure, that stabilises the body in the flow. And thirdly, if the body is moving slowly along with the flow, then again that's enough to stabilise the situation. This second case is a more nonlinear one. So here the body has been assumed to be in the viscous wall layer, viscous-inviscid nonlinear wall layer. It's an ellipse, head down, that the flow is from left to right. It's a shear flow in this case, uniform shear flow. And what have we got? So we've got boundary layer equations, unsteady boundary layer equations on either side of this obstacle. And then the body moves in response according to Newton's second law. Mass times acceleration equals force. I theta double dot is equal to the torque. The torque and the forces are due to the pressure from the fluid flow. But of course, as the body moves, that affects the fluid flow as well. M and I here are scaled mass and moment of inertia. H is height of the centre of mass. Theta is the angle about that centre, about the centre point. And as time goes on, so it starts life there at time about 0.1, and then the interaction forces the body down, and it hits the wall, bangs it onto the wall at a time of about 0.9, just there. And then we're still working on trying to analyse what's going on as that closure occurs, but it's clear that there's a small region of lubrication theory just close by, but the major response over the whole length scale is inviscid and produces eddies to the side. Basically, as that body touches down, the mass flux has to stop in those two regions, and that produces the eddying. Here's the third case with Ted Johnson himself looked at of small bodies, shorter bodies in the channel flow, and again that proves to be unstable. Okay, what I'd like to finish off with the next 5-10 minutes is this question of an escape velocity for a body perched on the ground. It's peanut shape in 2 dimensions, perched on the ground, and then the wind starts to blow, or the sea starts to flow. Atmospheric pressure is 0, but velocity suddenly is 1. Then the question is, does the body take off, lift off from the surface, and then after that, as gravity kicks in, will it come back to the surface, or will it escape? Will it fly away? Okay, so we're assuming that the layer involved is thin, at least at small times. It's that sort of situation. Okay. Motivations are from atmospheric problems, but also more mundane problems like leaf blowing and dust blowing, deserts, and this sort of arid effect afterwards. The governing equations we were looking at are thin layer equations. There's a bit too much here, but this is the these are the shallow water equations essentially. So that's the kinematic condition. Capital H there is the gap width at any particular time. It's given by the unknown body shape, underbody shape f of x, plus the displacement h of the centre of mass, and then the rotation about it. So h and theta are unknown. That's the kinematic condition. Then there's the momentum equation written there, as you might imagine. dp dy is neglected, so we're neglecting the gravity effect in the fluid, but it's there in the Newton's second law for the body motion, as written there. So again, the pressure force is giving the torque and the force, and the neglect of gravity in the fluid flow equations valid if the particles are relatively heavy. What else have we got here? Well, I just point out that the condition at the front is a Bernoulli condition that p plus half rho u squared is equal to rho over 2 as we jump across the leading edge or the front of the body region. And then at the rear end, there's a cutter-like condition, or the pressure must be atmospheric at the rear end. Okay, we can do some small-time analysis just to see if the body will lift off, and that's quite interesting. The development of the height is what goes like t squared. There's a subtlety near the contact point, so like t squared. There's a little region near the contact point to sort out. But anyway, some bodies do take off, and then some return to ground, as shown here. So the height h started in this graph has started there. It's gone up a bit and then bangs down again on the on the ground. But let's take a look at large time and the question of whether the body can escape from the ground. So looking at the equations, the asymptotic behaviour suggested is simply t squared. H and theta goes like t squared times h2 and theta 2, and the velocities and pressure become order 1. So going back to the governing equations, so that's going like t squared, that's going like t squared. The body shape becomes irrelevant. So from now on, what we're talking about applies for any shape of body at all, in principle. Also, because h is growing like t squared, the dh dt becomes negligible compared with that guy, and du dt becomes negligible as well. So at large times, the governing equations are becoming quasi-steady and are quite easy to solve. UH is a constant, and this UUX is minus PX, so you get the Bernoulli relation holding all the way through the gap at large times. Okay, and then substitute those properties into those two equations to see if H2 and theta 2 come out to be positive. Here are some cases. Yeah, these are cases which do show the t squared growth. Numerical cases, and again, when we work out H2 and theta 2 and their dependence on the scale of gravity g hat, we get this graph here. H2 and theta 2. Sorry, the combination of H2 and theta 2 is just right for liftoff, but until g hat equals 1/2. In fact, it's mg hat is equal to 1/2 is the cutoff. If mg hat's greater than 1/2, then this type of escape can't occur. Again, you can sort of see that quite fundamentally. So we've got at the marginal case where H2 and theta 2 are 0, so escape isn't quite going to occur. these two terms become negligible, and in the pressure here, the pressure this now holds for all x. The pressure maximum is going to be 1/2. That's the maximum the pressure can be. So this pressure force becomes 1/2. The length scale has been normalized to 1. So that's why there's this cutoff at mg equals 1/2. It's quite nice to convert that to dimensional form, which we're trying to do here. So the prediction is that the flyaway or escape will occur if this quantity here is greater than twice the density ratio. The notation's awful, but D denotes dimensional quantities still, and B denotes body properties, F is fluid. So this is the density ratio here, and this is like a Froude number squared. So the Froude number squared must be greater than twice the density ratio. If that happens, then the particle can be blown off the surface. What have we got here? The Froude number is based on the effective thickness of the body, HdB. That thickness is defined by this quantity. It's essentially the in 3 dimensions it would be the volume of the body divided by its planform area. Okay. Yeah. So that's the criterion then. Oh, and this is about neglect of dp dy. Yeah. Solutions. Skip. I think it's time to finish. Yeah. So the overall conclusions then, talk about the particle problems and then the patch problems before them, is that these local analyses apply over quite a wide range of scales. Both the patch and the particle can induce instability or transition. For particles, there's this stabilization in at least 3 ways. Whether there's relevance to sea mechanics is still to be decided, sea ice mechanics. Theoretically, of course, there are lots of extensions which could be done, but guided by what would be useful for the applications. Okay, I'll finish there. Thank you.
Any questions?
I did not understand what does it mean by the patches being unstable. Does it mean that it's starting to wrinkle up, or does it mean it's going to split up into? What does that mean by instability of the patch?
That if they're slightly disturbed, then if the oncoming shear is at a critical value, they will pop up. They'll be much higher than they should be, than you might expect. Whether they'll go on and wrinkle or not, I don't know.
Looks like you need to have a wall this analysis. So I wonder, for example, if you have an oil spill, you have patches of oil in the middle of the ocean. Would this theory apply?
I think if you can consider the airflow as if flowing over a solid body. So if the ocean isn't moving much and the wind blows, then it is effectively this situation, I think. Okay, as long as the oil responds in a certain way.
Yep. Just clarification. It's a single patch that you're studying, isn't it? You don't look at an assembly of patches.
Mostly the single one. We have looked at an assembly as well. Yeah. And
when it comes to the lift-off, did you use the shallow water approximation for the analysis throughout, or did you use other things too?
We used shallow water approximation throughout.
Right.
Yeah.
Without allowing for curvature of the surface.
That's right.
Could be important.
Yeah. Okay. Okay.
Equations by Bob Dressler that might be considered. I don't know if you've
yes, I'd be glad to know those actually.
Right.
I mean that criterion that came out involving the Froude number is it seems so simple that have an awful feeling somebody must have found this before. So I'd be glad of any guidance on
Well,
that.
basically, this allows for the surface curvature in the flow.
Yeah.
His
Okay.
equations, yeah.
Yeah. Yeah.
I think, have you done any
Well, yeah.
experiments to verify your prediction for liftoff?
None at all. No. This has come in the last couple of months. Yeah.
Are you planning to?
It'd be nice to. Yes. Got any suggestions? Be very grateful again for suggestions on how. In fact, there's been a lot of work on. We've done a lot of work on this dynamic fluid-body interaction, and we've found very little experimental study.
Just a question and then a comment. So the fluid flow past the flexible surface becoming unstable. I'm trying to think of an analogue for sea ice. So I'm guessing you're thinking that the ice sheet is flexible and you have a strong wind flow across the ice sheet. So if you have a strong wind flowing across land-fast ice, level land-fast ice, you're thinking you may cause a deflection in the surface, which will then affect the momentum transport from the air to the surface. Is that what you're thinking of?
Yes.
Or that could be an example you're thinking of.
That sounds a good candidate. Yeah.
Okay, all right. My comment was going to be that last bit about the peanut blowing off the ground.
Yeah.
Isn't that just the same as the Shear's criteria, which is using sedimentary flow calculations?
That's good. I don't know. Good.
Well, the Shear's criteria is used routinely for sedimentary flow and is used in sea ice for fragile collecting situations which fragile collecting at the surface.
Okay.
And it's basically the same equation at the end that you just derived.
Okay, I'll happily check that. Yeah. Well, happily is a bit of an exaggeration, but I'd be glad to check that. Yeah. No, thank you.
Okay, let's thank Frank again.
Yeah.